Yes? Good? Cool. So welcome to what I'm calling juggling chainsaws, not because there's anything particularly dangerous about unikernels, but because there's a lot of sharp edges that we'll be talking about. So I'd like, if you could tweet your questions to me. There should already be a tweet up that has a link to, or there should already be a tweet up where I mentioned, please reply to this tweet to send your questions. So I want to make sure I collect everything. I want to make sure I'm not biased against like whoever is quickest at raising their hand or whoever has the shortest question, because sometimes the most interesting questions are from the quiet people in the back. So go ahead and respond. Go ahead and please put your questions there if you have them during the talk.
I have a question. What's your
Yes.
Twitter handle?
It's on the bottom of the screen, JXXF. Cool. So so go ahead and put your questions there if you would. Really briefly about me, I work for a company called Pivotal. Pivotal makes a product called Pivotal Cloud Foundry that I work closely with. I'm a technical advisor for Pivotal Cloud Foundry, and we also have two other divisions, Pivotal Labs and Pivotal Data, but I mostly work with the two parts on the right there. So unikernels for me, when I first heard about them, it feels a lot like where containers were in 2013. We're still kind of figuring things out and exactly how it's all going to play out. And it's kind of a brave new world. A lot of tooling around unikernels doesn't exist, just like a lot of tooling around containers didn't exist tooling around containers existed, but not necessarily around Docker. And Solomon Hykes gave the thing that kind of kickstarted it for me was when he gave the PyCon talk in 2013, and I was scheduled to give a talk at a conference that had nothing to do with infrastructure, nothing to do with containers. It was actually about a e-commerce piece of software called Spree, and I was slated to do a talk about something called AWS OpsWorks, which is a technology or an Amazon Web Services service where you can build stacks really quickly. And when I saw Solomon's talk, no offense to Amazon, but when I saw Solomon's talk, I was like, I'd really like to switch my talk to be about containers because this sounds amazing, and I'm kind of getting the same feeling now when I think about where unikernels are. There's a lot of possibility, there's a lot of potential, and it's really exciting for that reason. And I don't think everything, as we'll see, I don't think everything is quite there yet to use it in production right now, but that was true of Docker in 2013 and for a while afterwards. So I think that there's a lot of reason to be optimistic and excited about unikernels, and I want to share with you some of those things. But first, before we get into that, just a quick show of hands. How many people would feel comfortable describing what unikernels are in a sentence or two? And don't worry, I won't call on you. I'm just curious, or people that would be, okay, so like maybe a third. So when I did a survey using, Google has this thing called Google Consumer Surveys where you can, instead of a paywall on your site, so if you run the Wall Street Journal, instead of requiring people to sign in, you can make them answer a survey instead, and they get to read the content. So I paid $11 to do a Google Consumer Survey, and I interviewed 1,100 developers, people who self-identified as I'm a developer, I'm an engineer, and then correctly answered a question about what Docker was. And then if you pass that sort of screening test, then I asked you these three questions. So the second question I have for you was, have you, or is anyone on your team, or you yourself, have you actually played with unikernels? That could mean, downloading something, maybe you haven't actually done anything with it yet, but you've taken some step towards trying it out. So just show of hands on taking some step towards trying it out. Okay, cool. So I had 11% come back from the survey with that. I mean, is anyone actually using unikernels in production right now? Really? Oh, are you from Docker? Okay. I would be interested to talk to you afterwards about how you're using it. So I got 0% from the survey said that they were actually using unikernels in production. So interesting overall in terms of how it broke down. There's at least some interest, but maybe people aren't exactly sure about how to get started, and that's understandable because it's a new technology. So I want to kind of walk you guys through why you should care about unikernels and what they are. So if you think about kernels, why are kernels important? Well, remember that time that you found a really cool ringtone on the internet and you were like, hey, I'm going to put that ringtone on my computer, I want to play it and hear what it sounds like, and then your computer exploded. Remember that? Or remember that time you downloaded that awesome cat GIF and you wanted to show it to your significant other, and you put it on their computer, and it ran out of memory trying to download all the frames of the GIF, and then your computer exploded again. That didn't happen, right? So that's because of something called hierarchical protection domains, which is just a fancy word for privilege levels in a kernel. And your kernel, pretty much every kernel has execution modes in which it treats some kinds of code as trusted or privileged, and other kinds of code as not so trusted or unprivileged. And in traditional architectures, the most trusted zone of code is called ring 0. So anything that's executing in a ring 0 context is closest to the hardware. And your kernel is responsible for, in large part, communicating with the hardware on behalf of some entity, that typically a person who wants to use that hardware, use that device to do something useful, like show a cat GIF, or play a sound, or move their mouse, or sample from their display or their video card, and so on. So the kernel is responsible for managing all that traffic. There are other levels above ring 0, not surprisingly numbered rings 1 through 3. It turns out that most processor architectures tend to support really just privileged and unprivileged, and then the degrees between 0 and 3 are used more or less by different operating systems. Most of the time on Linux, for example, you're really just using 0 or 3. There isn't a lot of room. There aren't a lot of things that use 1 or 2. So 0 and 3 are the areas that we're concerned about. And we typically think of code that executes in rings 0 through 2 as being kernel code, and stuff that executes in ring 3 as being userland code. So this is all the stuff that you write, bash scripts, Node.js applications, your web browser, all of that's executing in ring 3. And sometimes that ring 3 stuff needs to do something that's privileged, like read from a protected area of memory, modify a piece of hardware's firmware, that kind of thing. And then it'll be going through the kernel to do that. And so it'll be going to a escalated privilege mode where it can execute more stuff. So there's a sort of a way for your code to execute privileged code in a very specific controlled manner. And your kernel does a lot of the heavy lifting here, right? It gives you device drivers, process management, memory management, system calls, all kind of essential features of running an operating system that are required for everyone's idea of what a modern operating system is. So unikernels are, see, the word kernel is in unikernels, right? So there's a special way that we're going to use the kernel in a unikernel system. So if you first think about a conventional operating system stack, it probably looks something like this. You've got some hardware, you've got a kernel, you've got some services that are provided by the kernel and libraries that sit on top of it, and then you have your application processes, so your database, your web browser, your video games, et cetera. So the kernel handles the system calls, the process management, the stuff that's interacting with the hardware. And the services layer handles things like making it easier for applications to use higher level primitives to interact with the kernel. So for example, if you want actor-based concurrency or whatever, you might have a library that does that for you. That might be a service that your OS provides rather than something that lives in the kernel. And traditionally, we think of the services block plus the kernel block as being the operating system. So those two pieces combined are what we think of as an OS. Now, in a virtual machine kind of paradigm, you wind up with a process that you'd like to virtualize, to isolate in some way from everything else that's running on the same hardware, on the same machine. And what that typically means is that you copy or you get a different kernel and a different services layer and an entirely different OS, and then you run your process on top of that. So you're copying a whole section of the OS and then running your application on top of that. So virtual machines, not surprisingly, tend to be slower than booting up the native hardware that they're running on, because you have to virtualize all of those system calls through another kernel level, and then they get to talk to the hardware. So they're kind of duplicating all the work of the OS and the kernel that already exists on your system, right? There's already a services layer here. There's already a kernel layer here. it would be nice if we could reuse those. And sometimes we can't because they're two totally different operating systems, and the application, in this case, the Z application, is a Windows application, and the services and kernel layer that are running beneath that are Windows OS stuff, not Linux or not OS X. So they won't be able to talk to each other. So virtual machines achieve isolation through duplicating the effort of a kernel or a services layer and then combining that into an OS, and then virtualizing. They get performance benefits by trying to minimize the amount of stuff they have to virtualize and trying to pass through as much as possible. So containers do one step better. Containers replace the part that says kernel there with kind of a hook into the real kernel that they're running on. So there really isn't there sort of is a kernel, but it's not necessarily there. It's a hook into the real kernel in sort of a bare bones container. And so it gets to delegate kernel calls that it otherwise would have made to the shared system kernel. So if you've got some process that's running inside a Docker container, that container can take advantage of the fact that you're running in an environment that already has support for isolation in that kernel itself. So you don't have to do all of the work that a VM has to do for isolation. You can get a lot of the same benefits through process isolation services inside the kernel. So that does require that the kernel you're really running on to be aware of how to isolate those processes in a sensible way, and it has to have those kinds of hooks in them. But it does mean that you get to save part of the work that you would have had to do as a VM. Unikernels go one step farther, and they're based on the observation that if you look at a container, there's still a lot of stuff there, right? Like if you download a Docker image for the Ubuntu base image, whatever, you're downloading hundreds of megabytes, right? There's a lot of stuff in that blob because you're downloading an entire operating system. And your application is probably not using all of the things in that operating system, and it probably doesn't need every single thing that's in that OS, right? So just by way of example, here's my this is my computer, and I'm just going to list all the pieces of firmware that are on my OS right now. And there's a whole bunch of stuff that, like, clearly I'm never going to use. Like, I don't even have, I don't know what TI connectivity is. That sounds like it's a calculator. I don't have an AMD GPU. I don't have any Marvel network cards. I don't know what Liquid I/O is, but it doesn't seem like I need all of these things in order to, run a terminal or or accomplish useful things. So unikernels are predicated on this idea that, hey, maybe we don't need all of that stuff. So what if you didn't need all of the services layer and all of the kernel layer? What if you could just pick the pieces that you actually needed and then run your application that way? So you kind of get a super small container that only knows how to do one thing, and the only thing it knows how to do is boot and run your application. And if we could do that, that would mean that your entire application collapses to a single machine image that can only do one thing, which is run your application. It can't start another process. It can't, it literally cannot do anything else because only the calls in the kernel and the services layer that are available, the only calls that are available are the ones that are relevant for your application. So the application is the kernel in a sense, right? The application and the kernel are the same thing. They're all part of a coalesced machine image. It would be like if Microsoft distributed Windows 11, but the only thing Windows 11 did was run MySQL. You couldn't boot into Windows 11 and change the color of your desktop because there is no desktop. The only thing it does is start a copy of MySQL that then someone else can connect to. So you have one application, one kernel, and that's the promise and the premise of unikernels. So it sure seems like there's a lot of magic happening with respect to that. And the way that this works under the hood is that, in broad strokes, I don't have time to go into everything, but all of those pieces that you care about are passed through a compiler, which then decides in some way what your application is actually going to need out of the kernel and out of the services layer. So something needs to know how your application is going to consume those system calls And something needs to be able to trace all the possible paths of your application so that it can decide you're going to need this system call, but not this one, so I can throw that out. And you're going to need this library, but not that one, so I can throw that out. And then eventually you get some set of only the libraries and only the system calls that you actually depend on. But of course, there's a lot of magic happening in the purple circle here, right? Like, how do you decide if something is eventually going to call a specific library, right? So right away, you're probably thinking languages like maybe Ruby won't be so great for a unikernel world because it may not be obvious until runtime that you actually need some system call. So it might be harder to decide what you're actually going to use in cases like that. And we'll see in a second that the earliest attempts at doing unikernels have focused so far on statically typed languages where effectively the entire path of the program can be known at compile time. So are unikernels, so that's what unikernels are. Now, are they ready to be used? So first, let's talk about what's actually available. So the biggest and I would say kind of most central source of information right now is a website called unikernel.org. And this is the host for the original paper that was published, I think, in 2014, called Unikernels, the Rise of the Virtual Library Operating System. And they call it Virtual Library Operating System. And what they mean by that is it's as though your application depends on a library which is itself an operating system. So it's like you imagine you're a dependency manager, whether that's Maven or a gem file or a Node.js list of packages or whatever. You can imagine that you just added a dependency that said everything I need packaged into a kernel, and then that's effectively what happens from the perspective of your application. That's what they mean by a virtual library operating system. From your application's perspective, nothing really changed. It's still doing everything it was doing before with some changes maybe to how it was doing those things, but it's still doing all the same things. It's still ultimately calling into the same kernel, but it's only calling into a kernel that has the pieces that it needs. So unikernels.org or unikernel.org is the, does that say unikernels? I actually don't know what unikernels.org is. I'm curious to see. All right, that's something else. Okay, cool. So unikernel.org, right? The most interesting part that you're going to want to check out and that we'll talk about in a second is the project section. And here is where you can actually get started if you want to try out unikernels. So again, because it's still pretty early days, not all of these projects are like so great with documentation. It's not necessarily obvious how you get started, and how you get started is also totally different for all of them. The three most promising ones to look at are rumprun, which is a rump kernel. We'll talk about that in a second. RajOS and Ling, and also HowVM. I think I'm saying that right. I'm saying HowVM. I don't know if they pronounce it differently. So HowVM, Ling, MirageOS, and rumprun. Remember those four, and those are the ones you'll want to check out later, I think. So what's possible with unikernels right now? So one of the more interesting features of unikernels is that you can get extremely short-lived processes. That sounds stupid or bad in some way, or like, why do you want your process to be extremely short? But this enables a kind of architecture that I'm calling process per request. So you can imagine a web server that's really minimal, but exists only to spin up processes that are instances of your tiny, tiny web application. And then they only last for the lifespan of a single request. And now normally that would be crazy to do because it takes a long time to boot up a heavyweight process or a heavyweight VM, and you can't afford to wait hundreds of milliseconds or thousands of milliseconds to respond to to start responding to a web request if you're any kind of production system. But when the startup cost of your process or your unikernel process is 5, 10, 15 milliseconds, maybe it doesn't matter so much. Maybe if it's, and in some cases it's actually way better than that. We're talking about microseconds in the cases, in some of these cases. So you're basically paying the cost to launch a very, very tiny process, which is usually a very, very small amount of time. And if you can afford to do that, that means that you can afford to have thousands of simultaneous concurrent processes all accepting requests, all doing interesting things. And this is feasible right now, even today with rumprun, with some of the other unikernel projects. This actually is possible right now. Another interesting benefit is security, right? if you have a kernel that everyone is using, and an attacker wants to attack a process that's living on that kernel, then if they find one exploit for that particular version, then they know that that's applicable to everyone. But if you have a unikernel, your kernel is application specific. So they have to know something about your application in order to have an exploit against it. So we can't simply barrage you with exploits because the surface area that's vulnerable to exploitation is much smaller, right? You're not using a whole set of libraries or a whole set of features that you might otherwise be using, or might otherwise be in your application that you're not using. You know, how many times there are so many CVE exploits where it's like someone sends a PDF, and then the thing that triggers the payload is that it's like a sound library in a totally unrelated part of your operating system that gets called somehow and has a buffer overflow bug, that sort of stuff. So this eliminates really an entire class of problems that might otherwise exist with respect to the security of your application. And because your application is a special snowflake, exploits that work against one particular kernel won't apply. Even if someone gets you specifically, they won't be able to scale that exploit to other people who might be running similar kernels to you. Because again, the surface area isn't just smaller, it's also totally different per application. So if you want to, I showed you a few examples of the unikernel operating systems you could start using to try to play around with things. A few of them are language specific, so they require knowing Haskell or OCaml or Erlang if in the case of those three. And I was going to be mean and have a slide here where I said that something was OCaml, but it was actually Haskell. I mean, see how many people noticed, but I decided not to do that. So, so the hard part there is making sure that the facilities that you want exist in that language, or in that unikernel OS. So if you need, say, some kind of networking library or networking facility, then Ling or HowEM or MirageOS has to have that facility in it in order to do what you want. So if your application requires, say, making TCP network calls, if there isn't a TCP library in one of those three, then your application won't be able to work. And of course, your application would also have to be written in Haskell or OCaml or Erlang, as the case may be. The sort of alternative to that is using something called rump kernels, where you basically get you can get a POSIX kernel, so you can kind of run anything, but it's going to be cross-compiled. In other words, the compiler is running on an architecture that's different than the environment it's compiling for, right? Because it's compiling for this very specific kernel, and it might be, say, GCC or something, but it's compiling for an architecture that is over here that it can't see. So it has to, there's a step there that I think is tricky to get right if you're merging, say, Nginx and Ruby on Rails or something. You have to make sure that the way it compiles that is correct in the target environment. So that's the tough part about that. Another tricky area is that you're kind of on a strict diet. You don't have any of the tools that you might expect to see in a particular environment. You don't have fork, you don't have strace, because your application doesn't depend on strace or fork, right? And your application doesn't depend on syslogd or whatever. So if you want those things, you have to bake them into what you're asking for, otherwise you don't get them. So you have to think ahead about things like monitoring, logging, debugging, because you don't get them out of the box and they don't exist in the environment that you're operating in. And I think that the exciting part is that we may see things like totally new architectural paradigms for how you build software, just in the same way that containers enable people to think about things like Kubernetes and think about new ways of orchestrating workloads to make things that weren't possible before possible. I think we may see things like transient microservices. Microservices are popular now, but what happens when a microservice looks like a population of thousands of processes, all super tiny, running and starting, stopping in the span of dozens of milliseconds? And there's room for kind of a cautionary tale here, because we've seen problems before where stuff gets a little bit overhyped and super exciting, and it doesn't always play out. And two examples that came to my mind are software transactional memory, where we have, there was a really big push in the mid-2000s where everything was going to be software transactional memory, and STM is a kind of memory where it's kind of memory contract where you basically can wrap all changes to memory in a transaction. So it's like everything is in a database transaction, but in memory. And if that sounds like it's going to have a huge performance penalty, you're right. And we haven't been able to figure out exactly how to get that working. That was something that didn't quite pan out. Another thing it didn't quite pan out was fully homomorphic encryption. This is this idea that you can encrypt something, send it to someone. They don't know what it is, but they know how to do operations on the encrypted thing without knowing the contents of what they changed it to or from. So for example, this would be really handy if you wanted to send, say if you operated a overseas company and you didn't want people to know that you were funneling profits offshore, it would be super handy if you could encrypt your tax return, send it to the IRS that just does some operations, and they verify that that something is true about your tax return, but they don't actually know what's inside it. So that turned out to be kind of a pie in the sky thing. We haven't really figured out that either. So there was similar hype around these kind of like possibly revolutionary technologies, but it didn't really pan out. I don't think that's going to be true of unikernels, but it is worth mentioning that we have seen this kind of thing before. We should let the evidence come out. So the four big takeaways I want to point out are: it's very much worth checking this out. There are problems with it. It's not ready for prime time, but you should absolutely be taking a look at this now and making yourself aware of it. Definitely don't use it in production. So many of the facilities I think that we rely on today for orchestration, for managing these kinds of things, don't really exist for unikernels yet. There's a little bit of hype going on, but I think there's a lot of potential and there's a lot of room for optimism about the future of unikernels. And I'd be willing to bet that Docker didn't pay undisclosed amount of money for unikernel systems for no reason, right? There's probably, I think we can infer something from the fact that they bought a company whose entire purpose was academic research and interest in unikernel systems. So thanks very much to the organizers, sponsors, and attendees. That's you. I know how hard it is to put on a conference, and I'm grateful that you were able to have me here and put on a great show. Thank you, guys.